In this course, I teach the basic graph theory, and today in the second lecture, I'll discuss about the first theorem of graph theory, which is also known as Handshaking Theorem, and I will do some problems based on this theorem. So firstly, we will know what is the statement. So for any graph G, we have that sum of degrees of all the vertices of G is basically twice into E, when this E denotes the number of edges in G. Okay, so if E of G denotes the edge set of G, then the small e denotes the cardinality of E of G. The proof of this theorem is very much straightforward. I will give a quick hint of this proof. So the proof goes like this, that if we can take any edge, okay, any edge of this graph G, let's say this edge is U1, UV, so we can observe that each edge of G eventually contributes degree 2 to the total degree of the graph. So basically this sum of degree of V, when V is a vertex of the graph G, then this actually is the total degree of the graph G, right? Total degree of G. So for any edge we can take E1 or something, so it will ultimately contribute degree 2 to this total degree, because degree 1 this edge will contribute degree 1 to this vertex U and degree 1 to this vertex V. So eventually it will donate 2 degree to the total degree of the graph. And also if we consider in loop, so there is only one vertex associated with this loop. So if we call this to be E2 and this vertex to be, say, U1, then it will also contribute degree 2 to this single vertex. Okay, so here though we have only one vertex corresponding to this loop, but this loop is also contributing degree 2 to this single vertex. So eventually any edge we can consider in the graph G, and it will contribute degree 2 to the total degree of the graph, which is given by this sum. So eventually it is equal to, we can write that it is equal to 2 into E. Okay, so like this the proof goes. So, and if we consider this U and V to be two persons, then we can think like that these two persons are handshaking, then this E1 edge we are getting. So like that this name Handshaking Theorem is coming here into the picture. So now we will discuss a corollary of this theorem. So this corollary says that in every graph there are even number of vertices of odd degree. Okay, so now we will go to the proof of this corollary. So firstly we take a set S to be the set of all vertices of odd order. Okay, so odd order vertices, this set. Okay, so now since it is a corollary, we can say that using this theorem we will prove this corollary. Okay, so firstly what we have from this theorem, sum of degree of all the vertices of G is twice into number of edges of G. Okay, so now what we can write this sum of degree of V, we can write this like that sum of degree of V when V belongs to S. So now actually taking this set S, we are dividing this vertex set into two parts, S and S complement, that is the vertices which are in S and which are not in S. So like that we can write now that this sum is sum of degree of vertices when this vertex is in S, and sum of the degree of vertices when this vertex is not in S. Okay, so it is equal to twice E. So now as we can see from the definition of S, that these vertices, when a vertex is in S, then its degree is odd. So these degrees will be odd, and so if it is not in S, then this degree will be what? Even. Okay, so then this term is even because all of these degrees are even. When this v is not in this set S, then it is not of odd order, so it is of even order, and in that case this degree will be even. So in that case this degree, it will be the sum of the even numbers is always even, so it will be something like 2r or something, when this r is any integer, any positive integer obviously. So this is an even number. So now what we have from here, that sum of degree of v when this v is in S, okay, it is equal to what? 2e minus 2r, because it is also even, so we can write it like 2 into something, say w. Okay, so it is also even. Subtraction of two even numbers is also even. So sum of degree of v when this v is in S is an even number. Now what we have, that if v is in S, then this degree of v is odd. Okay, so we are adding some odd numbers and we are ultimately getting an even number. So what this suggests, that adding some odd numbers will get an even number if and only if this number of odd numbers is even. Okay, so there must be even number of this type of terms d of v. There must be even number of terms. Okay, so this number, or that is the cardinality of, has to be even, otherwise this sum will be odd. Okay, this has to be even. For example, say if we add 1 and 3, then we will get an even number, but if we add 1 and 3 and 5, then what we will get? That 1 plus 3, 4 plus 5, 9. Okay, always we will get an even an odd number. So adding odd number of odd numbers will get an odd number, but adding even number of odd numbers will get an even number. Okay, so from here we have that this cardinality of S is even, which suggests that number of odd order vertices is even. So here this proof of the corollary is complete, and using this corollary also we will do some problems to get the clear idea about this corollary. So now using the previous corollary we will solve this problem, that can you draw a graph with 6 vertices, of which 3 are of degree 5 and 3 are of degree 4. Now what the previous corollary said, that in any graph or number of odd degree vertices is always even. So here the number of odd degree, the degrees are here what? There are 3 vertices of degree 5 which is odd, and 3 vertices of degree 4 which is even. So number of odd vertices is here what? 3, which is an odd number, so it is not possible. So from the previous corollary itself we can say that it is not possible. In another way also we can solve it, that not using the corollary, from using the first theorem itself we can solve this, that here what is the total degree of the graph, that is the first theorem actually gives us that sum of degrees of all the vertices of the graph G is twice into E. Okay, so here what is this? So here what is the sum of all the vertices? It is 3 into 5 plus 3 into 4. It is equal to twice into E. Okay, so it implies that twice E is equal to 15 plus 12, so 27. So E is equal to 27 by 2, which is not an integer. So the number of edges is always an integer, so it is not possible. Okay, so it is not possible. So now we will solve another problem, that a graph contains 6 vertices, 2 of degree 4 and 3 of degree 3 and 1 of degree 5. So we have to find the total number of edges. Okay, so we will use the first theorem of graph theory, that twice into E is equal to sum of degree of all the vertices of G. Okay, so V of G. So here what is this sum? There are two vertices of degree 4, so 2 into 4, and 3 vertices of degree 3, so 3 into 3 and one vertex of degree 5. So 1 into 5. Okay, so what is the sum? 8 plus 9, 17 plus 5, so 22. This implies that E is equal to 11 we have. Okay, so we can draw a graph which has these vertices with these degrees, and this will have 11 edges. Okay, so now we'll know a new definition of k-regular graph. Okay, so what is k-regular graph? Any graph G is said to be a k-regular graph if all the vertices of G has the same degree k. Okay, so we'll see some examples of this type of graphs. So let us consider this graph on 3 vertices. Okay, so here all the vertices have degree what? 2. Okay, so all the vertices have degree 2, so this graph is a 2 regular graph. It is a 2 regular graph. Okay, and we will see another example. Let's say this one, the simplest one, and it is also a 1 regular graph. Okay, also we can consider a null graph like that. Here both the vertices have degree 0, so it is 0 regular. Also we can consider another graph like on 4 vertices. Let us consider this one. Here we can check that all the vertices have degree 3, so it is a 3 regular graph. Like that we can construct more examples in this way. Okay, so now we will discuss another problem, which is that find the number of edges in a 3 regular graph on 6 vertices. So again we will use the first theorem of graph theory, that 2E is equal to sum of degrees of all the vertices of G. Okay, so here what is this sum? This is a 3 regular graph on 6 vertices. So there are 6 vertices of degree 3. So the total degree is 6 into 3, which is 18. So from here we have that number of edges is 9. Okay, so like that we can consider more examples, and now we will discuss a problem when we have to draw a graph. Okay, so we will be given some degrees and we have to draw a graph if possible on these vertices with the given degrees, and the number of edges will be determined by the first theorem of graph theory. So our next problem is that is a graph with 4 vertices A, B, C and D with degree of A is equal to 4, degree of B is equal to 2 and degree of C and D are equal to 5. Is it possible to draw such a graph? If possible, then draw such a graph. Okay, so firstly we will check that whether such kind of graph is possible or not by checking the total degree is equal to twice into E. So firstly twice into E is equal to 4 plus 2 plus 2 into 5, which is equal to 6 plus 10, so 16. So such a graph is possible, and when the number of edges will be 16 by 2 is equal to 8. Okay, so such a graph is possible. Such a graph is first of all possible. So we need to draw such a graph. Now there is many ways to draw such a graph, and we have a way, since this graph may contain a loop or may not contain a loop. Since the degrees are given to be this degree of C and degree of D are 5. Okay, so firstly we have to check that whether there are some odd degree graphs or not. So the easiest way to draw such a graph is that we will check that whether there is a odd degree vertex or not. If there are some odd degree vertices, then we know that there will be even number of odd degree vertices. So we will firstly take these odd degree vertices. So here odd degree vertices are C and D. So we will join them. Okay, we will pair them actually. If there are more odd degree vertices, then we will make pair of these odd degree vertices. Here we have made a pair of C and D, and we have joined them through an edge, and we have gotten this edge CD. Okay, so now this the rest of the degrees of C and D are what? For C there are even more for C there is degree 4 left, and for D there is degree 4 left. Okay, so we can draw some loops to get this extra degree. Okay, so we have to draw 2 loops here to get degree 5 for C, and also here also we will draw 2 loops. Okay, so now degree of C and degree of D both are 5. Okay, so degree of C and degree of D we have already shown that they are 5. Now we have another 2 vertices A and B, and we have to make A of degree 4, so we have to draw 2 loops here. So now degree of A is 4 and degree of B is 2, so we need to draw 1 loop only. So degree of B is 2. So it is the easiest way to draw a graph. If a graph possible, then we can draw a graph like that. So and this drawing is not unique, so we can have another drawing, like actually more than one drawing we have. So for example, this graph we can draw it like, and here we have B, and degree of A is here, 4. So degree of C, it is C, so degree of C we have gotten to be 5, and degree of D also we have to make 5, so already we have 3, so we can add one more loop here. So now degree of D is 5. Okay, so degree of D is 5. Now degree of A, we have to make degree of A to be 4, so we can add here one loop and an edge. Okay, so now degree of A is 4 and degree of B is 2. So like that we can draw, we can actually have more drawings for this graph, so these drawings are not unique. So in the next lecture we will probably discuss about subgraphs and all, and we will discuss more about degrees and simple graph and etc. So thank you for watching me. Please consider subscribing if you like the video and if you want more videos on graph theory. Thank you.